Hello there, Khaled Al here. We talked previously about the MPU 6050, but something that we didn't mention is that the MPU 6050 does have a DMP, a digital motion processing. Now, the idea of the digital motion processing is slightly harder to understand in terms of a coding perspective. However, the simple idea is that the digital motion processing is an implementation in the MPU 6050 that allows to the device here or the peripheral, so in this case the IMU, to use the data and do some calculations with it. It is mostly used to determine things such as the yaw, roll, and pitch. If you are aware of those, quite important in terms of designing an airplane. However, how we're going to use it today is just to print out the X accelerometer as well as the gyroscope X, Y, and Z axis data. I will show you how to use it. However, before I get started, I do recommend the simple method of using the get the raw value and just dividing by the appropriate value to get the normalized degree or meters per second or G value. In but and it is if you are trying to use the digital motion processing to determine whether it's the yaw roll pitch or uh, trying to determine things well in a different orientation scale or maybe even a different um, just not accounting gravity. Those are all quite important and more useful to use the digital motion processing with. Nevertheless, let's get started. So here we have the code for the MPU 6050 DMP reference. As you will notice here, we still use the wire and the I2C development library. In this case here, we also use the MPU 6-axis motion amps version 6.12 for the DMP here. Now, something to note is that if you did install the MPU 6050 as per the prior use of this implementation here, you do not need to download any extra library. It is included as part of the library. Something else to note about this here is that we will be using an interrupt. As such, if you're not allowed of how an interrupt works, I recommend that you go watch the previous video about the interrupts and the switches, interrupts, and the watchdog timer. So in this case here, we are next declaring some global variables. We are declaring a volatile MPU interrupt. All that variable would do here is that each time the DMP is ready, it will send an interrupt signal through the interrupt pin here, and then that will just declare it as true for code that will be used inside the load loop that we'll see in a few minutes here. And then we have the packet size. The packet size is the amount of data inside a buffer. How you should think, it's a set data. So it's a set data by the MPU. So what I mean by that, it's a constant variable or a constant number, and it's about 42 bytes usually. And that just accounts for all the data from the X, Y, and Z axes that will be pulled up from the FIFO buffer, which I'll get to in a few minutes as well. And then in this case here, this is not really necessary, but why I included it is that you could determine the actual interrupt state based on the register on the DMP. What I mean by that is each time the DMP calls in or sends in an interrupt, it also flags a register, or pretty much it just has another value inside of it that turns to 1, which you could use. It and or you might just keep it how it is right now, and that's how we'll do it just for simplification purposes. And then here we have a Boolean that just says is DMP success. That is just for the setup, as there's a lot going on, so sometimes it does lag. So just make sure that you just make sure that the code doesn't go even if the DMP wasn't successful in setting up. Next here, we just have a few definitions. So the interrupt pin, as I mentioned, is on 18. Recall that you cannot use any pin. There is some specific pins that you can use in the interrupt. In this case here, we're using 18. And then we are declaring the accelerometer offsets, and then the gyroscope offsets. Next here we're declaring the serial. We're initializing the serial communication here. And then, of course, we start initializing the MPU by first calling the wire, making sure that the I2C communication is started. And then we initialize the gyroscope just as before. We test the connection. And then what we do here is we actually have to initialize the DMP. So we have to basically we tell the DMP that we're going to use it. So it has to power on and such. Another thing to note here is that it does return a value that will be stored in DMP init, or it's stored for initialization, and if it is successful, it returns a 0, which is important in a few lines here. And then we calibrate the gyro as well as the accelerometer. We set the offsets, and then if the DMP was successful, so if it's equal to 0, we'll just calibrate it once more just to set the offsets. And then, so just as fine tuning purposes, and then we will turn on the DMP. To turn on the DMP, all we do here is we set the DMP enabled, and then we will start it by saying the MPU interrupt is at false, because that is important, because then the minute that there is an interrupt that will turn it to true, then it will go to the ISR here, and then it will turn it to true. And then, of course, we're going to say that if that occurs, then if the DMP is successful and is going to evaluate to true here. And then what we do next here is we have to attach the interrupt. That is also important, and it makes sense as we need to actually declare where is the interrupt pin. The ISR will be called the DMP data ready, and it is going to be detecting on the rising edge. And then in this case here, we also will, for simplification purposes, as I mentioned, I'll just show it. Let me just show it again. That's how you get the int status, which you could use for the interrupt status. What this allows you to do is you actually have two checking now for the interrupt. Either you actually check the MPU interrupt, which is a variable you declared in your code here. Another one is to actually check the interrupt register on the DMP. So if you are not, you're not completely sure if the interrupt is actually true, if it's successful, then you could use that as just as a double checking, just as an end statement. And then we have here package size. As I mentioned, the package size will not change, but we do have to define it. So the DMP get FIFO package size is determined here, which is, if you recall, it's about 42 bits. And then here, if the DMP wasn't successful, there's two types of errors that you could get. Either an initial memory load fail, just means that there's not enough memory on the Arduino to load the device here. Another one is the DMP configuration update failed. This one is quite rare. Usually, if anything fails, it will be the initial memory load. All you have to do now, then is just reduce whether the type of memory you're running on, whether it's the SRAM or the flash. Then you have to make sure that you try and reduce memory usage. Now here we have a statement that if the DMP success wasn't successful, and if you recall the DMP success is turned to true here, then it is important to note that we do not have a false statement. So we probably should include it here and just declare this as false if an error occurred. So this is what we have here, and then so if that is false, then it will just end it. Return here is another way to end the void loop. It will never keep going again, just like while one that we saw in a previous video. Anyways, so after doing that, if the MPU interrupt has been turned to 1, in other words, that the MPU interrupt, in other words, the DMP launched the interrupt, then first thing we need to do is set back the MPU interrupt to false. That will allow us to receive in another data. And then once again, just mentioning throughout the code here where we could use it. So the actual end status here, we could use it again for our purposes here. And I should. So in this case here, I'm actually going to return the integer value for the actual int status here, as I want to show you how it is developed throughout the code here. And if I do launch the code without editing it, it will be incorrect. Nevertheless, so in this case here, we include the actual int status, and then we declare a few variables that we're going to use. Vector int here is vector int is as the name implies, it's a vector, so it holds in x and y and z value. So here we have two vectors that will declare in. We have the accelerometer vector as well as the gyroscope vector. And that will just store the x and y value from the FIFO that we'll see in a second here. And then we declare a FIFO buffer. A FIFO, just to mention here, just means first in, first out, right? So any data that comes in will be the first data that comes out. That's what a FIFO does. And it needs a FIFO needs to be implemented in code. What I mean by that is that when you you need if you build anything that uses a FIFO, and if you look into this further, you actually need to implement a FIFO of some sort, as just to make sure that every data you send in is the data that comes out first. In this case here, the library does include that, does create that, so you do not need to create it. All you need to do is just initialize initialize or declare the variable here with an array of 64. And then here we include the FIFO count. The FIFO count will just include the amount of data that has been processed by the DMP. Okay, and then we have our normal accelerometer and gyroscope variables. In this case here, this code is important. This code is if the FIFO overflows. In this case here, remember we have 64 index or the size is 64. If it goes past 64, it will overflow. The data will look extremely incorrect. What I mean, and then you'll most likely see it that X value will be significantly higher and Z value will be significantly smaller. So what that means is that everything shifted and that'll be an overall. So for what this code does is if it detects it, whether it's the FIFO count is bigger than 1024 or the actual end status and the actual end status is ended with the MPU interrupt FIFO overflow bit. What this statement really means, this whole statement here, is that if the overflow register has been flagged, so if the overflow register has been flagged, then this will occur. The actual end status here is just preventing it from resetting the FIFO unless you need to, because if you remove it, it might just reset the FIFO even though the DMP wasn't ready yet. So it was used this to reset it. So here, as I mentioned, we reset the FIFO, and then we also get the current data count, which should be 0, but it is important to do that if the DMP went through an interrupt right between. And then we have here if just another statement here. So remember that we called it at the beginning the MPU interrupt, and then we actually use the actual int status here just as a double checking method. And then if the FIFO count is not equal to the packet size, remember packet size is equal to the full amount of data that should be sent by the DMP. Sometimes not the whole thing goes through. So what we do here is we keep asking for data until it's full, and then we store the data inside the FIFO buffer, which is important. So first of all, here we declare the size of data that we'll store into the FIFO buffer. In this case here, we'll store if it's about 42, the packet size is about 42, the FIFO buffer is about 64. So you have a range here to almost prevent some overflow. But in this case, this is what the statement does. It takes in the data from the DMP and stores inside the buffer, and then we actually send in the address. This ampersand here is for the address. We send in the address of the accelerometer vector int 16 variable, and we also send in the FIFO buffer where the data was stored. What this will do is it will store the values of the X, Y, and Z accelerometer data to the vector inputs. What we do next, and we do the same thing with the DMP get gyro function here, which will do the same thing for the gyroscope. Notice how it divides by 16384 and 131. Those are values determined by the data sheet that will get them both to their respective units, whether it's G for the accelerometer or degrees per second for the gyroscope. Finally, here we just print it up and we will see the data here that it produces in a second. So first thing we do is we upload the code, make sure there's no errors, and it will save it. So there is no errors, it's currently uploading. It is done uploading. If we open the serial monitor here, just make sure the baud rate is the same, and then it's initializing. And here we go. If you see at the data here, you can see there is still some noise. And you can see here that the Y here overflowed. It should be around 0, as you will see down here. So the overflowing is quite natural in the DMP. That's why in many cases in the DMP, you have to account for them by either taking the average or creating a filter that ignores anything that is overflowed. As you can see, Z here also overflowed. If we go to a bit lower here, you can see that you get proper data. Usually, you should leave the DMP running so about 30 to 30 seconds ish to just to make sure that it's proper to the temperature and everything is set correctly. And after a while, here all the data seem to be correct. So that's what's important to note here, that it occasionally overflows, and it is important to account for that in code. Now, this is using the DMP to get the accelerometer, gyroscope, and data. But recall that the best way to actually do this is to not use this method here. The best way to actually do this is just use the get raw data. If you do want to use the DMP, the more popular method, or when people use DMP, if we just open under file examples MPU6050 and then go to this one here, MPU6050 DMP6 using DMP version 6, version 12, and we expand it, you can see here that there's a lot of implementations for the DMP that the normal or the raw data cannot do. In this case here, you can have an output readable quaternion, an Euler, a yaw pitch roll, which is the popular one, readable real acceleration. In this case, it takes in account the orientation, and then output readable word acceleration. In this case, this is relative to your initial orientation. And then we have an output teapot. The output teapot is it's a nice one to have. If you have processing and you try and launch this one here, you will have a 3D image of the 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 device here, or it kind of looks like a plane, a weird plane though. And then you can hold your IMU and move it around, and it moves with you. It's a nice way to see how the DMP works, because the DMP combines the data from the accelerometer and the gyroscope just to make sure the data outputted it looks correct. If we launch the code here, in this case here, that will pull out the yaw pitch roll, because that is the one uncommented. If we launch this to the board here, the sec we should see it. I think there will be an error though. Yep, the intro pin here is declared at 2. That should be 18. And it is done uploading. We can just open this here. Now this baud rate here is set at 11500. In this case here, you send in the characters to start it. It will initialize the DMP. And this is the yaw pitch roll. So in this case here, the yaw pitch roll is based on several things. It stopped all of a sudden. What this happened actually is the data was overflowed, and then the DMP just decided that it was unable to keep going. It doesn't happen with any peripheral, not only the MPU6050. So if that happens, all you need to do is reset here. That's why it is nice to always implement a watchdog timer, especially if you have any I2C connections, because if they get stuck there, it will reset by itself. So yaw pitch roll is based on rotation, and it accounts a bit the speed of both here. So So as you can see here, it's a pretty powerful tool. There's not too much noise, as you can see here, but it does use a different style in terms of coding perspective here that may not be intuitive. Whether it's to send in some variables and then maybe reuse them to get some other data. It's quite different, but it is quite useful. So that was about the DMP here. As usual, if the reference code here will be available in the description. And I hope you found this useful, and see you in the next video.